Well, good morning, pre-calculus students. Welcome to a new week and our first video of the new week. Here we are going to go into the next section of Chapter 8. We are going to be looking at 8.2, which is going to be studying the conic section of ellipses. So it is a conic section, just like we have been looking at, but it's specifically a conic section known as an ellipse. Okay, so what is an ellipse? Well, I'm going to show you a diagram here. If we were in school, I would build the diagram on the whiteboard. And in this case, I'm just going to have to do it here. So pause the video as you need to sketch these things down. And then I'm going to go on right now and describe what these things are. So as you go, you might want to listen to it. My suggestion would be listen to the description once, pause, sketch it on your own, sketch down all the important things, and then listen to it again. Okay. So an ellipse obviously looks similar to a circle. It's a closed curve that goes like that, but it's not exactly a circle. The truth is, a circle is actually a specialized type of ellipse, and we'll look at that when we see the equation. So what we see, though, is because the ellipse is not completely circular, it has one axis here where it has its longest distance through the center, and it has a shorter axis here, which is the shortest distance through the center. And so the longest distance through the center, we call that the major axis, going between vertex to vertex. It actually has two vertices, one at each end of that major axis, and then these axis, the line that goes through that. So the major axis is a line segment. Okay, it just starts at the vertex, goes to the vertex. The focal axis is a line that goes through the center and the vertices. The center is located, as you would guess, in the center. And then, of course, if we call this the major axis, we call this the minor axis. It's the smallest distance from side to side through the center. And then the other thing, when we're in a parabola, we had a single focus and a single vertex. Here we have two vertices, and we also have two foci. So that would be the plural of focus. We don't normally say focuses, we say foci. And so we have the two foci there. Now, that's the parts of the ellipse. Now what we have to do is we have to now quantify them. In other words, when we want to describe the ellipse, we want to express these distances in quantities. And so to do that, we have to know, we have to pick some values we're going to call those quantities. So here's what we have. So now I've labeled the distance from the center to a vertex as A. A is what we call the semi-major axis. It is half of the major axis. If the major axis is going from here to here, then we see the semi-major axis is going from a vertex to the center, and we call that A in our formula. B is what we would refer to as the semi-minor axis. It's the distance from the center to this endpoint here of the minor axis. So that's the semi-minor axis. And finally, C in our formula is the distance from the center to a focus. So we just call that C. We don't have a special name for it. I suppose you could call it focal length, but we don't normally refer to that as, but that's what our C is it's the distance from the center to a focus. So we also label the center as HK. So just like the vertex was the key point in a parabola, and so we labeled it as HK, in an ellipse, the key point is really the center. It's not the vertices in the ellipse. It's really the center, and that gets our denotation of HK. So if you need to pause the video and sketch that and sketch those things down, go ahead and do that. But we're going to move on to understanding the ellipse in terms of its equation. So we're going to build a chart like we did with a parabola. It's going to have three columns. One column for the features of the ellipse. The other column will be for when the ellipse is horizontal. What we mean by that is the major axis is horizontal. This one that I sketched here would be horizontal. Vertical would be where the major axis is vertical. So the first thing we got to look at is we got to look at the equation. What equation are we going to use for these things? Well, if it's horizontal, the equation looks like this. We have x minus h squared plus y minus k squared, and then that x minus h squared is over a squared, and the y minus k squared is over b squared. Now, the distinctive things about this, it doesn't, because this is plus, it doesn't matter which order these come in, but the key thing is, remember, A is the semi-major, B is the semi-minor. That means what you have to do to figure out whether it's horizontal or whether it's vertical is look for where the bigger value is. In this case, the A has to be bigger than B because it's semi-major versus semi-minor. So we know that it's horizontal when the bigger denominator is under the X. Vertical looks just the opposite. Notice now the bigger denominator is under the Y. And it doesn't matter what order you put these in, you look for which one has the bigger denominator, the X or the Y. If the X term has the bigger denominator, it is horizontal. If the Y term has the bigger denominator, it is vertical. So other than that, notice it's just like a parabola. The K pairs up with the Y and the H pairs up with the X. Notice in this case, much like a circle, since it's a closed curve, both the X is squared and the Y term is squared. So we have both of them being squared. And in fact, we can see that I told you that a circle is a special type of ellipse. Well, as you can probably guess, you can think maybe what could I do to this equation to make it a circle? Well, it's what you would guess. A circle, it's the same distance from the center to the edge the entire way around. So if you made your semi-minor and your semi-major the same value, if A and B are equal, you have a circle. You would just multiply both sides by whatever that value is, and that becomes your r squared over there. All right, now let's look at some features of this. So vertices, how do we find the vertices? Well, we know we start with our center, and we know that a vertex, if we look here, is A away from the center. So what we have to do, if it's horizontal, is that's going to change the x coordinate. So we take that h and we add a to it to get one of them, and we subtract a from it to move to the left to get the other one. The y value stays the same. K does not change. If it's vertical, it's the y value that's going to change. So we are going to add and subtract a from k. So we get two of them. We get h and then k plus a, and then h, k minus a. So two vertices. For foci, we're going to need two of those. Notice, once again, we start from the center. The center is the key point in the focus. This focus is C away. The other focus would be C away in the other direction. So just like this, here we added A to H. Now we're going to add and subtract C from H. K stays the same. If it's vertical, we add and subtract C to K. H stays the same. Now, there is a special relationship called a Pythagorean relationship because it follows the same relationship as the Pythagorean theorem between A, B, and C. Now, the one thing is it doesn't exactly follow the way we're used to seeing the Pythagorean theorem, because if I look up here at my ellipse, if you can see my ellipse up here, notice which is biggest between A, B, and C. Well, I think you can see pretty clearly it's got to be A. So it's got to act like the hypotenuse of the right triangle. B and C are shorter, they are like the legs. So our relation is A squared is equal to B squared plus C squared. So the two smaller sides of the triangle, when squared, add up to the larger side of the hypotenuse. Same thing here. The two smaller distances, the B and the C, when squared and then added together, add up to A squared. And it doesn't matter whether it's vertical or horizontal, because those A's, B's, and C's are designated based on the orientation of it. It's the same relationship. Okay, let's use this information to answer some basic questions about these things. So, number 5 gives us the following equation. It gives us 4x squared. I need to open up my book here. Whoops. Revealing extra stuff there. Not that you won't eventually get to see it anyway here, but sometimes it's more distracting if I just show you a bunch of stuff and then you're busy writing it down instead of listening as much. So number 5, what it wants us to do is find the vertices and the foci. So we need to get it in its standard form. That way we can pick out the H, the K, the A, and the B, and then figure out the C. So notice the standard form, there is a 1 on the right side for a constant. Here I've got 12. I don't want 12. So I will divide both sides by 12. That will give me a 1 over here. Distributing this 12 in as I divide both of those by 12, I get 4 over 12, which is x squared over 3, plus, in here I get 3 over 12 is 1 over 4, so I get y squared over 4 equals 1. Now this is a standard form for an ellipse. Now it's pretty easy to pick out h and k. Nothing is added or subtracted from the x and the y, so we know it's centered at the origin. H and k are both 0. So that's pretty easy. So I found the vertex. Now I have to find the foci, which means I have to find C. Well, notice I've got my a squared and b squared. By the way, which one's a squared? That's right, it's this one. It's not this one, even though, so a squared can come second, it's got to be the bigger number. So a would be 2, b would be square root of 3. But a squared is 4, b squared, so that makes a2, like I said. B squared is 3, that makes b radical 3. So a squared is equal to b squared plus c squared. So solving that, I see that c squared is going to equal 1. So if c squared is going to equal 1, then I can know my vertices are going to be, notice I have to go a away from my center, so I add, subtract 2, and add 2. Notice this one is vertical, because the a squared is under the y, so I add and subtract from the y coordinate there. And from the foci, it's positive and negative 1, which I'm not sure why I didn't write that down there. This makes, when I solve this here, that makes c equal to positive and negative 1. I can maybe write that. C equal to positive and negative 1, like that. So there's our vertices and there's our foci. All right, let's look at another one. This is number 15. So it gives us this equation, and it asks us to, in this case, sketch a graph of the ellipse by hand. So what you want to do is you want to find the center. You want to find you don't need to worry about the focus. You do need to find, it's actually in some ways easier to sketch than a parabola. You find the center. You need to find where your vertices are. And then you need to find where the endpoints of the semi-minor axis would be. So you need to go B. You need to know what B is. So looking here, I see in this case, my a squared is 16, which makes my a 4. My b squared is the smaller one. It's 4, which makes my b 2. Notice my center here is going to be at x coordinate negative 3, y coordinate 1. So I'm going to go here and I sketch this. I go x of negative 3, so I go back 1, 2, 3, y of 1, plot my center right there. Then, since this is horizontal in nature, and my a is 4, I go horizontally 4 to the right for one of the vertices, and then 4 to the left of the center for the other vertex. And then get the other endpoints here, the endpoints of the semi-minor axis, I know it's 2 away from the center because b is 2, so I go up 2, down 2, plot those points, and then I sketch the curve that goes through those points. Doing the best job to sketch the curve. Okay. Your homework is 8.2, 2 through 20 even. Hope that goes well. Remember, we have a Zoom session today. By the time you get this, probably we already had started the Zoom session since it starts, I think, in about 15 minutes from right now. Okay, we'll talk to you guys later. Bye.